Basic data. U is the force function of attraction field. O is the attraction center. The vector field has the distribution of intensity. Its Newtonian potential field. Point B has the vector of velocity as shown at the picture. The question: what is the evolution of point B? What is the trajectory of point B? Let's search the vector of intensity AI. The gradient from force function U is the vector AI. Its covariant vector with evidence shown at proof early. The distribution of vector has the form: draw the velocity vector with scale. Next, draw the radial axis R1 and build the vector of intensity A1. Draw the Frenet serrate TN frame and do the projection A1 on normal axis. TN frame projection on normal axis. From the start point of vector, draw the straight line that connects arrow of vector velocity v1 with the start point of intensity vector an1. And I have commutator of covariant direction. Again, this line is the commutator of covariant direction. In other words, it's the generalized direction of future speed v2. In other words, it's radial commutator as it's shown earlier. In this place appear the questions: what is the invariant or modulus of the future speed? What is the point of action of future velocity? In other words, where is the transversal commutator? The answer demands to use the principle of least action. Write the Lagrange function as it's necessary for principle. The Lagrange function consists of difference scalar function. T is the kinetic energy. The kinetic energy is bilinear form on velocity vectors. In other words, it's sum of the square of velocities. Its sum of invariant is expressed by metric tensor. This sum multiplies on mass invariant. In this example, the mass is equal 1. U from R is the scalar force function that describes the influence on square of velocity vector. It depends from direction. In this case, is radial direction. It's well known that phi is the cyclical coordinate. Therefore, in this direction isn't the action on velocity. The contravariant component of angle velocity isn't changed by the first function. The force field influences only the radial direction. Therefore, the square of radial velocity is changed by the force function. Build the graphic of distribution of the invariant intensity vector from radial coordinate. The arrow of velocity vector shows the opportunity change in radial coordinate without action from field. Its point B-2. This radius is defined by graphical method as shown at the picture. On the other hand, the point B-2 can receive the projection of velocity vector on radial axis R1. Its radial velocity in point B1 without action from field. However, the field doesn't depend from speed because the action from field can be defined as the difference square of radial velocity. The square of vector VR02 shows the opportunity of field between coordinate R1 and R2 to influence on square vector VR1. It case to become clear if use the Lagrange equation. I don't stop on this trivial moment. The square of vector VR02 is defined as definite integral from the scalar function of intensity vector field. The limits of integration are radius 1 and radius 2. The integrated square is the square of vector VR02. The difference between the square of velocity vectors give the square of invariant of radial velocity vector VR2 in point B2. Difference point B2. Draw the radial velocity vector along the radial axis R2. The start of radial velocity vector is the point B2. Through the point B2, draw the axis that is parallel to the commutator of covariant direction. The axis goes to the across with normal axis. Its commutator of invariant velocity. In other words, its transversal commutator. In this case, commutator defines the invariant of velocity vector v2. Invariant of velocity vector v2. The trajectory of point B goes near the commutator axis and the velocity vector v1. In points b1 and b2, the trajectory line tangents the vector of velocity and the axis of commutator. 1 point, 2 point tangents commutator vector line. As the same, in the point B2, the trajectory line tangents the velocity vector v2. This happens because the point B2 is the point of transformation. Tangents B2 points of transformation, commutator to velocity. In that way, the problem has been solved by the CTM. This example gave opportunity to see how the city M contains the set of methods and theorems. I would say that the covariant tensor machine is the resumptive method of differential geometry and description geometry. Also characterize variation and other knowledge. I think the covariant tensor machine can help to answer the question in physics, techniques, and mathematics. But this is the subject of a future conversation.